this is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we'll discuss about the multi-level NAND or NOR implementation. So in this, we will be talking about how to convert an Aoi logic. What is Aoi? Aoi stands for AND or invert logic into NAND logic, and how to convert an Aoi logic into NOR logic, and some examples on NAND NOR implementation. So first of all, why to study this NAND or NOR implementation? So as we all know that NAND and NOR gates are universal logic gates. NAND and NOR gates are universal logic gates. What do you mean by universal logic gates? So universal logic gates means any logic can be implemented using these gates, that is NAND and NOR are said to be universal logic gates which can be used to implement any of the digital logic. So which is not possible with any of the other logic gates. So that is why we are now learning how to implement this any logic function or any Boolean expression using NAND or NOR gates. So first of all, we'll be discussing about the procedure for converting an AND or invert logic into NAND or NOR logic. That means any logic can be implemented using NAND or NOR circuit is our aim. So how to convert an AND or invert logic circuit into NAND or NOR implementation? So first of all, what is this first step? Draw the logic circuit for any given Boolean expression. I want to realize that Boolean function using either NAND gate or NOR gate. So for that, the first step is to draw the logic circuit using AND or NOT gates only. So for the given Boolean expression, first draw the logic circuit using AND or invert or else NOT gates. And then if we have chosen NAND logic, that means if we want to implement the Boolean expression using NAND logic, then the next step is we add a circle, or else we can also call it as bubble. Okay, so add a bubble at the output of each AND gate and at the inputs to all the OR gates. So what is this next step? If we have chosen a NAND logic, that means if we want to implement the Boolean expression using NAND gates, then the second step is to place a bubble or a circle at the outputs of AND gates. That means at the output of each AND gate, how many AND gates it may have. At the output of each AND gate, we need to place a bubble, and also we need to place the bubbles or circles at the inputs of all the OR gates. And then, for example, if this is the case when we have chosen NAND logic. If we have chosen a NOR logic, then what we have to do? It should be reverse. That means we have to place or else add a circle or bubble at the output of each OR gate and also at the inputs to all the AND gates. So in the previous case, that means in the NAND logic, we have I have said you that place a bubble at the output of AND gate and at the inputs of each OR gate. But in case of NOR gate, it is reverse. That means place the bubbles at the outputs of OR gates and at the inputs of all the AND gates. Okay. So this is the second step. First step is draw the Aoi logic or else AND or invert logic. Then place the bubbles according to the logic chosen. That is NAND logic. Place the bubble at the output of AND gate and at the inputs of each OR gate. And if NOR logic is chosen, place the bubble at the output of OR gate and bubbles at the inputs of each AND gate. Once it is done, then add or subtract an inverter on each line that received a circle. So that means we can add or subtract an inverter, that is nothing but a NOT gate, on each line which has received a bubble or circle. So in the second step, we have placed the bubbles, right? We have added bubbles. So whatever the line that has received a bubble, we need to add or subtract an inverter. And and also we need to eliminate double inversion. We need to eliminate double inversion. Double inversion means what? Double inversion means, so if we have two inverters in a single line, so if we can eliminate this kind of double inversion. Why we can eliminate this kind of double inversion? If, for example, if I consider A as input, the output of first NOT gate will be A complement, which is given as input to the second NOT gate. So A complement whole complement is again A. So that means there is no difference if I place two inverters on a single line. So that is why if we come across any double inversion in a single line, then we can eliminate that double inversion. So what is the third step? So add or subtract inverters on each line that has received a circle and eliminate double inversion. So why? Because the double inversion leads to the same signal. So that is why we are going to eliminate the double inversion, and hence the polarity will not change. And finally, the final step of this NAND or NOR implementation is we need to replace each inverter, replace all the inverters with NAND or NOR gates. Depending on the logic chosen, we need to replace the inverter with NAND or NOR gate. We need to replace the inverter with NAND or NOR gate, comma, bubbled OR gate with NAND gate in case of NAND implementation, and also bubbled AND gate with NOR gate. What do you mean by bubbled OR gate and bubbled AND gate? So we were placing the bubbles at the input side of OR gate in case of NAND implementation, and AND gate in case of NOR implementation. So for example, let us consider bubbled OR. What does it mean? Bubbled OR is nothing but a gate which and it is an OR gate which have received bubbles at the input side. So for example, my inputs are A, B. Then what is the output of this one? So always you remember, whenever you are drawing the circuit, the bubble indicates inversion. So before applying it to the OR gate, A is getting inverted because we have a bubble here, and B is also getting inverted. So what does it mean? If we are giving A bar as input to the OR gate and B bar as input to the OR gate. So that is A bar plus B bar. I can also write this one as A dot B whole bar. So by applying the De Morgan's law, how can I write this one? A dot B whole bar can be written as A bar plus B bar. So that means here this is nothing but NAND logic. So here the bubbled OR gate is producing the same output which is equivalent to NAND gate. So that is why I can replace this bubbled OR gate with NAND gate. Bubbled OR gate with NAND gate. Similarly, bubbled AND. Bubbled AND means AND gate which has received bubbles at the input side. Okay, so we have bubbles here A, B. So what is the output of this one? A bar dot B bar, which I can also write it as A plus B whole bar. So applying the De Morgan's law, I can expand this one as A bar dot B bar, where De Morgan's law states that whenever you are taking a complement, the variable will be complemented, and also plus will be changed to dot operator and dot will be changed to plus operator. So that is what I'm applying the De Morgan's law, and we have plus symbol here, so it will be changed to dot, and we have A here, it will be complemented, so A bar dot B bar. So that means the output of this one is identical to A plus B whole bar, which is nothing but NOR gate. So that is why I can replace this bubbled AND with NOR gate. Bubbled AND with NOR gate. So that is what I said. So in the final, whatever the inverters we have, we need to implement them using either NAND gate or NOR gate, depending on the chosen logic. And also bubbled OR should be replaced with the NAND gate, and bubbled AND is replaced with NOR gate. So this is the procedure for conversion of AND or invert logic into NAND or NOR logic. So here now, first of all, let us see. We have exclusive OR gate, exclusive NOR gate. So the first problem is, or else first example is, implement exclusive OR gate and exclusive NOR gate using uh, uh, sorry implement exclusive OR gate and exclusive NOR gate using NAND and NOR gates here. So first of all, what is an exclusive OR gate? So XOR is also represented like this, exclusive OR. So whose symbol or else logic gate, logic symbol is this one. Sorry. Okay. So the exclusive OR gate symbol is this one, exclusive OR, right? So here this is XOR gate AB. If AB are the inputs, then the output C, let us consider. C can be written as A XOR B, which can also be written as A bar B plus AB bar. This is exclusive OR. And coming to the XNOR, okay? Or else first let us see the exclusive OR gate implementation using NAND and NOR logic. So here this is my exclusive OR gate. Now first of all, I am implementing this using NAND implementation. So in case of NAND implementation, what is the first step? The first step is to draw the logic circuit that is using AND, OR and NOT gate. So here C is equals to A bar B plus AB bar. This is my XOR gate Boolean expression. Now I want to implement this one. So it is A bar, okay, A bar, okay, and here B, and we are giving it to an AND gate. So A and B. So what is the output of this one? A bar B. And similarly, we have A B bar. A bar B plus A B bar. These are given to an OR gate. This is the first step. Okay, this is A B, right? This is the first step, implementation. Implement or else draw the Aoi logic. Aoi logic, right? This is the first step. So here C is equals to A bar B plus AB bar. A bar B plus AB bar. Now coming to the second step. What is the second step? The second step is we need to place the bubbles at the outputs of each AND gate and at the inputs of OR gate, because we have chosen NAND logic. The step 2, in step 2, place the bubbles at the outputs of AND gate and at the inputs of OR gate. So add bubbles. So we need to write it in detail. Bubble at the inputs of OR gates, because we have chosen NAND logic, right? OR gate and outputs of AND gate. Outputs of AND gate. This is the second step, right? Now what I am doing, I am going to draw the circuit again after doing the modification. So what we are doing, we are placing the bubbles at the outputs of the AND gate. So this is an AND gate. So we are placing the bubble here. So this is A and this is B. And now we are placing again, it is an AND gate. So we are placing a bubble at the output of the AND gate. And now we have an OR gate at the output side. So we are placing the bubbles at the input side of the OR gate. So this is the second step. This is also A and this is also, this is B, right? Now coming to the third step. What is the third step? Third step is add inverter. I'm going to add or subtract. It is a step, right? So I'm going to add here. Add an inverter. Add a NOT gate at the on each line which has received which has received bubble, which has received a bubble. So now I'm going to add an inverter. So now the third step is, so this line has, is this first line got any bubble here? No, so that is why we no need to place any inverter here. And even this line also not received any bubble. Whereas this line has received a bubble here, so we need to place an inverter. And this line also received, so even though these are same, so as this has received two bubbles, we need to place two inverters here. So the first line did not receive any bubble, so no need to place any inverter here. But at the output of the AND gate, we have to place a inverter, because it has received a bubble. And even at the input side of OR gate, it has also received a bubble, so we have placed an inverter. So this inverter is for this bubble and this inverter is for this bubble. Okay, this is AB. Now coming to the next one. So we have, again, we don't have any bubbles at the input side of the second AND gate, so no need to place any inverter here. And similarly, as we have received a bubble, as this AND gate has received a bubble at the output side, we are placing an inverter at this line, on this line, and also we are placing one more inverter. So this is for this OR gate, okay, which has received bubbles at the input side, right? So now here this is A, B. So now this is a single line, right, which has received two inverters. So eliminate double inversion. Even this single line is received two inverters. So eliminate double inversion. Eliminate double inversion. Okay, so if I eliminate double inversion, and then after eliminating the double inversion, replace all the inverters with NAND gate and bubbled OR with NAND gate again. So now the fourth step is replace inverters and bubbled OR gate with NAND gate. With NAND gate. This is the fourth step. Now after doing that, so I can draw the circuit like this. So bubble inverter is nothing but a single input gate. So how can I implement this one using NAND gate? I have to take a NAND gate which is having two inputs. Just tie these two inputs together so that I can implement an inverter. So that is what we are doing here. So I'm taking a NAND gate and I'm tying both the inputs together. And this is a NAND gate, and then this is A, B, and we have one more inverter. So just draw the symbols properly. Okay, and here we have, this is A, this is B, we have an inverter here. Okay, and then we have eliminated the double inversion. So no need to place any inverters here, and this bubbled OR gate should be replaced with NAND gate again. So this is the implementation of exclusive OR gate using NAND gates. Now let us verify whether the output is same or not. So what we are getting here, A bar, this is B. So A bar dot B whole bar. This is the output of first NAND gate. Okay, next this is A dot B bar whole complement, and then again these two are multiplied here. So here A bar dot B whole bar dot A dot B bar whole bar. Right, now expand this. So if I expand this, so what I'll get A bar dot B bar plus A dot B bar, right? So this bar and bar get cancelled. So that is A bar dot B plus A dot B bar. So this is the answer here. This is anyhow identical to this one. So that is how we have implemented. That means for implementing an XOR logic gate using NAND gates, how many NAND gates are required here? 1, 2, 3, 4, 5. 5 NAND gates are required. Similarly, you can also implement this XOR gate using NOR gate. I'm not going to discuss this one. I'm giving it as assignment to you. Just implement XOR gate using NOR. Now I will be telling you about okay. Uh, so okay. So let us implement this one. XOR gate. So again, C is equals to A B bar plus A bar B. So here now I'm using NOR implementation. I'm doing this one using NOR. So here NOR implementation is done. First step. What is the first step? Draw the Aoi logic. So draw the Aoi logic means we need to have A. This is B bar. Okay. And this is AND gate. This is A, B. And next A bar, B. So this is A bar and B. Anyhow you can represent A, B. Right. And finally we have an OR gate. Okay. This is an OR gate, not AND gate. So this is the OR gate. C is equals to A bar B plus AB bar. This is the first step. Now in the second step, what we will be doing? Place the bubbles at the outputs and inputs of OR gate. Right? So now we are placing the bubbles at the outputs of. So here, what is this logic? NOR logic I have chosen. So now I am placing the bubbles at the inputs of AND gates. And also this is A, B. And now again it is an AND gate. So I am placing the bubble at the input side. Okay. And at the output side of OR gate. This is the second step. A, B. This is NOR implementation. Reverse we need to do. Now coming to the third step. What is the third step? Place the bubbles place the inverters on each line which has received a bubble. So this line has received a bubble. So we need to place a inverter. So we are placing an inverter as this line has received a bubble. So already we have an inverter and we are placing one more inverter because it has received a bubble here. Right? So this is the first AND gate. Now coming to this one, already this line has inverter and this has received a bubble. So we are placing one more inverter here and we are placing an inverter for the bubble. Okay. And then is this two lines received any bubble? No. Only we have bubble at the output side. So that is why we are placing bubble at the output side of the OR gate. Now coming to the fourth step, eliminate double inversion. So this is a double inversion we are eliminating and replace the inverters with the NOR gate and bubbled AND with NOR gate again. So now here, so as a double inversion got eliminated. So again, inverter with the NOR gate is this one. Okay, as a double inversion was eliminated and this bubbled AND gate should be replaced with NOR gate. Okay, this is A, B. And now coming to this one, this is again A, B. Double inversion got eliminated. So no inverter is there. And whereas this one is replaced with NOR gate. And we have to replace the bubbled AND with NOR gate. And anyhow, we have an inverter. We have a NOR gate here. And this inverter again should be replaced with a NOR gate. So this is A, B. Now let us verify whether the output is identical to this or not. This is A bar. This is B bar. So now what I'll get? A bar plus B whole bar because it is NOR gate, right? This is A plus B bar whole bar, right? And then what we will get? The output of this one is A bar plus B whole bar plus A plus B bar whole bar whole bar. And finally, we have complemented. So what we will get finally, complement, I'll get it as A bar plus B complement plus A plus B complement because it is double inversion, it is eliminated. Now expand this one, A bar whole bar, this plus becomes dot into B bar. Okay, and this is plus again here, A bar dot B bar whole bar. So what I'll get? This becomes B. So A dot B bar plus A bar B. So this is my exclusive OR. So this is the implementation of exclusive OR gate using NOR gate. So this is the procedure here. I hope it is clear. Now you can also that means for implementing exclusive OR gate using NOR gate, how many gates I require here? I have to use 1, 2, 3, 4, 5, 6 NOR gates. Okay. So now we are going to implement exclusive OR and exclusive NOR using NOR logic. Okay. So that is what I have told you here. So what I have done, I have implemented XOR using NAND and I have implemented XOR using NOR also. So I'll be telling you the XNOR only. I'll tell you XNOR using NAND. XNOR using NAND. Then you have to do about you have to do the XNOR using NOR you do. So here first of all, what is XNOR gate? XNOR gate is nothing but the symbol of XNOR gate is this one. XOR, not of XOR is XNOR. This is XNOR, AB. So what is this one? A XOR B whole complement. I can also write this one as AB plus A bar B bar. This is my output C. Now the first step using NAND implementation. So first step using NAND implementation, draw the Aoi logic. What is the Aoi logic? This is the Aoi logic for the implementation of AB. So now, this is the Aoi logic for the XNOR gate. So this is AB and this is A bar B bar. So what is the output? AB plus A bar B bar. This is exclusive OR gate. Right? So now, the second step is, as we have chosen NAND logic, so place the bubbles at the input side, output of the AND gates and inputs of the OR gate. So now I am placing the bubbles here. Okay. So this is AB. Already we have a inverter. We have an inverter here. Sorry. This is NAND logic, right? So NAND logic, we need to place the bubbles at the outputs of AND gates. Outputs of AND gates. And at the inputs of, OR gates. So this is the second step. Now coming to the third step, what we need to do, place the inverter at the line or else on the line that has received a bubble. So is this line received a bubble? No. So that is why no need to place any inverter on the first two lines. Whereas these two lines also did not receive any bubble. So no need to place any inverter. Right? Now, this line has received a bubble for AND gate and also at the input of OR gate. So, two inverters we need to place and two inverters we need to place here. And is this line received any bubble? No. So, that is why no need to place any inverter. So, we need to check each and every line whether it has received a bubble or not. So, after the third step, so we are placing an inverter here and we have already an inverter. We have already an inverter on this line, and as this bubble is there, now we are placing a bubble here, an inverter here, and we are placing one more inverter because the OR gate has received bubbles at the input side. So this is the circuit after the third step. So now this line has received double inversion and this line also has received double inversion. So this is AB and this is also AB. So eliminate double inversion and replace the inverters with NAND gate and bubble door with NAND gate. So now fourth step. So here now we have a NAND gate here. So this inverter is to be replaced with NAND gate and this inverter is also should be replaced with NAND gate, and finally we have a NAND gate and then we are placing a NAND gate here. So AB. Now let us verify the output here. What is the output of this one? A dot B whole complement, and this one is A bar B bar whole complement, and finally the output of this one, this is A bar we are getting and this is B bar we are getting, right? And finally we will be getting A dot B whole bar dot A bar, B bar, whole bar, whole bar. So this is C. So C is equals to, now I'm expanding this one, A, B bar dot A bar, B bar, bar, whole bar. So I'm expanding this, A, B bar, whole bar. So as we have dot operator here, as I'm expanding the complement, so this becomes plus now, A bar, B bar, whole complement, whole complement. This complement get cancelled. So finally I'll get AB plus A bar, B bar. So this is the XNOR gate. So XNOR gate is also represented like this, or else we can also write this one as AX or B whole complement. So this is the NAND implementation of XNOR. So you try for NOR implementation of XNOR. So it is very easy. Okay. So now let us see. Let us take one example here. So this is the Boolean function. Not only logic gates, we can also implement any Boolean expression using NAND or NOR gates. So right. So now I'm taking the problem here. What is that? I want to implement a function AB into C plus D. AB into C plus D whole complement plus A. Okay. So this is my Boolean expression. So now I want to implement this one using NAND and logic. NAND or NOR logic. First I want to implement using NAND gate. So that is NAND implementation. So first step. What is the first step? So the first step is Aoi logic. Aoi logic. So I want to draw the Aoi logic for this circuit. So what is that? First I am taking A, B and I am giving it to an AND gate, and then C, D and I am giving it to OR gate. So this is CD and this is AB. What is the output of this AND gate? This is AB and this one is C plus D. And then I am giving these two as an input to AND gate again here. AND gate. So that is AB into C plus D. And I have to get the complement. So for that I am using an inverter. And finally I am taking A. Okay. And then I am giving it to an OR gate. So this is the output. So what is the output here? A plus AB into C plus D whole complement. This is the logic circuit, Aoi logic circuit for the given Boolean expression. Now coming to the step 2. What is the step 2? Place the bubbles, add circles or add bubbles. Okay, so add bubbles. So what is the logic? I have chosen NAND. So at the output of each AND gate and at the inputs of each OR gate. So how many OR gates we have? 2 OR gates we have and 2 AND gates we have. So that is why I am taking an AND gate and I am placing the bubble at the output side. So A, B. And then as we have an OR gate here, we are placing the bubble at the input side. And finally we have one more AND gate. So place the bubble at the output side. We have an inverter. Okay. And then we have an OR gate. So OR gate we have. So we are placing bubble at the input side. Okay. So this is the step 2. Coming to the step 3. Here we have to place inverters on each line that has received a bubble. So this line did not receive any bubble here. So no need to place an inverter. So whereas the second line also did not receive any bubble, no need to place any inverter. Whereas this and the OR gate has received the bubbles at the input side. So we are placing bubbles here. Sorry, inverters here. So this is the third step. And then are these two lines received bubble? This line has received a bubble, output of AND gate. So we need to place an inverter. Okay. And then this line did not receive any bubble. So we are using an AND gate here. Okay. And then as this line has received a bubble, so I need to place an inverter. Already we have an inverter in this line. So then we are going to place a bubble here because OR gate has received a bubble at the input side. So this line also must have an inverter. Okay, so this is the logic circuit. So then double inversion, we have a double inversion here. Eliminate any other double inversions, no other double inversions, so only double inversion is there on that line, so we have eliminated that. Now replace all the inverters with AND gates and bubble door with NAND gate. Okay, so now here the final circuit is, this is anyhow it is a NAND gate, so we have an inverter here, so we need to use an NAND gate here, and this is also an inverter we have to use, and this is a bubble door we need to use. We need to replace that bubble door with NAND gate, and anyhow we have an inverter here, so we need to use an AND gate, and then we need to then eliminated this line is eliminated, this double inversion is eliminated, and this inverter should be replaced with NAND gate, and we have one more line, so which have again an inverter, so this bubble door is replaced with AND gate, NAND gate. So this is the circuit A, B, C, D. So if you verify the output, again you will get the same output, which is nothing but AB into C plus D complement, C plus D whole complement plus A. This is the output you will be getting. So this is the implementation of given Boolean expression using NAND logic. Okay. Similarly, we can also do it for NOR logic. We can also do it for NOR logic. Now the second thing is NOR implementation. NOR implementation. So if you have any doubt, you can just verify the output of this circuit. Okay, so this is AB, that is AB bar, and this one is C bar, D bar, that is C bar, D bar, whole bar. Okay, or else we can also write this one as C plus D. We can also write this one as C plus D. Okay, and this one is AB whole bar, right? AB whole bar, whole bar. So what we'll get? AB here we'll get. So that is AB into C plus D complement, and here we are again complemented here. So what I'll get? I'll get AB into C plus D, right? And what about this one? I'll get A bar here. So what is the final output? I'm going to get C is equals to AB into C plus D, okay, into NAND gate, right? Into A complement, whole complement. So then finally expand this one, AB into C plus D whole complement plus A. This is the output. So that is the implementation. Like that, if you have any doubt, you can just verify the output of this gate, this circuit, whether it is equivalent to the given Boolean expression or not. So as it is equivalent to the given Boolean expression, this implementation is correct. So similar way, I'm going to implement the same given logic, that is F is equals to AB into C plus D whole complement plus A. So I want to implement this one using NOR logic, right? So the first step, what is the first step? Aoi logic. Already we have drawn the Aoi logic. Again I am drawing it. AB into C plus D. This is C plus D. And then we are giving it to an AND gate. And then we are using an inverter. And finally we are using an OR gate. Okay. So this is AB. This is CD. Finally the output will be AB into C plus D whole complement plus A. This is F, right? So now the second step, NOR logic we have chosen. So what should we do? At the inputs of AND gates and at the outputs of OR gate, we need to place the bubbles. So we are placing the bubbles at the inputs of AND gates and at the output of OR gate. So this is the OR gate. We are placing the bubble at the output here, A, B, C, D. And again we have got an AND gate here. So we need to place the bubble at the input side of OR gate, and we have an inverter, and then we have an OR gate here. So at the output side, we need to place the bubble. So this is the second step after adding the bubbles. Now coming to the third step. What is the third step? Now place the inverters on each line which has received a bubble. So this line received a bubble, so I am placing an inverter. This line also has received a bubble, so I am placing an inverter. And this is a bubbled AND gate, AB. Now coming to this one. So this line does not receive any bubble here, so I am not placing any inverter here. Okay, this is CD, right? And then again, this line has received a bubble. This line also has received a bubble. So I'm placing an inverter here, and also I'm placing an inverter here. And this is my bubbled AND gate, right? And this line does not receive any bubble. So now this line also did not receive any bubble here. Okay. And finally, we have NOR gate, whereas this line has received a bubble, so I'm placing an inverter. Any double inversions are there? No double inversions are there. So we need to keep all the inverters. Now, finally, the fourth step, replace all the inverters with a NOR gate. So this is my inverter. I'm going to replace this one by NOR gate. And this is also one more inverter. Replace it by using a NOR gate. Okay. And replace the bubbled AND with NOR gate. So this is a NOR gate, right? And this is an inverter. We are replacing this by NOR gate, right? Now, coming to the second one. So we have only a NOR gate. So this is a NOR gate, CD, and this is AB. Whereas this has received an inverter. So I want to replace this one by NOR gate. And finally, we have a bubbled AND, which is to be replaced with NOR gate. And already we have a NOR gate here. So now I'm going to use this as a NOR gate. Whereas finally we have one more inverter. We need to replace that using NOR gate, right? Now we can also evaluate the output of this logic circuit, so that you will be getting the same expression, AB into C plus D whole complement plus A. This is what you will be getting. So what is the output? A bar, B bar. So this one is A bar plus B bar whole bar. So what is the output? I'll get AB. What about this one? Because A bar plus B bar whole bar, if I apply the De Morgan's law, A bar whole bar, this plus will be changed to dot, and B bar whole bar, that is AB. We will be getting AB here, whereas this one is C plus D whole complement, and it is again complemented here. C plus D we'll be getting C plus D here. And what is the output? It is given to complement. So this is one. So now what is the output of this one? AB complement in plus C plus D whole complement. So what is the output of this one? And finally it is again complemented. Finally it is again complemented. So now sorry, here this is this one, whereas this one is plus A whole complement, plus A whole complement. This is the output of this one. So finally I'll be getting this one as AB complement plus C plus D whole complement plus A complement complement. This one will go off. So now I'm expanding this one. AB complement complement, plus will change into dot, and this one is C plus D complement. Okay. Finally, I'll be getting this one as AB whole complement will be AB into C plus D whole complement plus A. So this is the output we are going to get. So this is how we can realize any Boolean expression using NAND or NOR logic. So as the NAND and NOR gates are universal logic gates, so any logic can be implemented using NAND and NOR. And the only thing is we need to remember the conversion procedure from Aoi Logic into NAND or NOR logic. So by using that procedure, you can convert any logic, any complex logic into NAND implementation or NOR implementation. So that's all for this lecture. I hope it is clear to you all. Thank you, Anindra.
Like, share and subscribe. Hit the bell icon for more updates.